Welcome back, ladies and gentlemen, to another video with Mr. Kenton. We're going to be continuing our discussion with looking at solutions, and we're going to be focusing in on specifically solubility. How do we form saturated solutions, and talking about concentration as well. And so as we begin, I want us to review some things that happen in the solution process. Now, the first thing that we're familiar with is we understand that if you're dealing with a solid solute, what we know that happens is that solid solute dissolves in the solvent and the solution forms. Well, there's a reverse process that's also taking place called crystallization, and crystallization is essentially the solution breaking down and the solute no longer being dissolved in the solvent and reforming its solid within the solvent. Okay? Now, both of those processes are taking place, and depending on the conditions, crystallization is going to occur if there's too much solute present, and so then it doesn't dissolve. Dissolving is going to take place if not enough has been dissolved in the solution, and so the solute is going to be converted into a solution. Well, saturation occurs when crystallization and dissolution as processes are in equilibrium. And so when I say equilibrium, what we're really looking at is that the rates of those processes are equal. Doesn't mean that the amount that's dissolved or that's crystallized are equal. It simply means that the rates of those two processes are the same. Okay, that's going to be an important concept and principle, equilibrium, when we talk about that later. Just wanted to introduce that to you here now. Now, solubility, by definition, is the amount of solute that's required to form a saturated solution. And so a saturated solution is going to form when the crystallization and dissolution processes are at equilibrium. So when no more of your solute can dissolve in your solvent. Now, there's a supersaturated solution, which is a special type of saturated solution that forms when you take a solution that's been saturated, you heat it, you dissolve more solute, make sure it's completely dissolved, then you cool it to a lower temperature, and you keep the excess solute dissolved in your now lower temperature, right? So you've essentially, in some senses, you've kind of tricked your solution into dissolving more than it can handle. Now, supersaturated solutions are much more unstable, and so the tiniest addition of solute is going to cause all of the excess to recrystallize and get back to that equilibrium position. Okay, now let's take a look at some factors that influence solubility, because there are some things that we can do to cause the solute to dissolve more favorably in our solvent. And the first thing I want us to take a look at are solute-solvent interactions. Now, what we know is that polar liquids tend to dissolve in polar solvents. And this has to do with the fact that they have similar intermolecular forces. Right? This is why you can get miscible liquids. They're going to mix in any proportion. You take a polar liquid like alcohol, place it in water, and it mixes. It doesn't even look like you've got two different liquids. It looks like one liquid that's been combined. Now, immiscible liquids, these are liquids that do not mix in any proportion, and they create distinct layers. And so I want you to think about like oil and water, for example. If you've ever seen those little columns, what happens? You have water and oil, they don't mix, and so they separate out and they create these distinct layers. Now, the reason for all this is because of intermolecular forces. As you can see, we started with intermolecular forces in this unit. We examined intermolecular forces in gases, and we're looking at them again here in solutions. So intermolecular forces are an extremely important component that we're going to be needing to understand what's going on in our solution process. Now, other things that can influence solute-solvent interactions, the number of carbon atoms in a chain, those affect the solubility. The more carbon atoms you have in your hydrocarbon chain, the less soluble it is in water. The number of OH groups on your carbon chain is going to increase the solubility in water. which leads us to a generalization of this idea that like dissolves like. So if something has London dispersion forces, it's going to be able to dissolve things that have London dispersion forces as well. If something has dipole-dipole interactions, then it can dissolve something with dipole-dipole interactions. If you've got something with hydrogen bonding, it's going to be able to dissolve something else with hydrogen bonding. And so to kind of quantify this, to help put this in perspective, the more polar bonds in the molecule, the better it dissolves in a polar solvent. So you think of it in terms of like dipole moments. The larger the dipole moment in the solute, the more likely it's going to dissolve in our polar solvent. The less polar the molecule, so you've got lower dipole moment, the less likely it's going to dissolve, the less it's going to dissolve in our polar solvent, and rather it's going to dissolve better in a non-polar solvent. And something else to consider, network solids, so things like quartz or diamond, they don't dissolve because of the strong intermolecular forces in the solid that cannot be reestablished in any solution that could be formed. Okay. Now, you might be thinking, Mr. Kenton, there's a lot of information here. You're going kind of fast. We're actually going to be able to take a look at some of these solute-solvent interactions more in depth. And so that's why I kind of went through this slide a little bit more quickly. So just kind of bear with me. If you need to, you can always pause this, rewatch it, and go from there. So let's look at this idea of like dissolves like first. So we can think of this as kind of like a rule. It's not like a guaranteed rule, but it's something that's real quick. And it just simply states that polar solvents dissolve polar solutes. And non-polar solvents are going to dissolve non-polar solutes. Again, this idea of similar intermolecular forces of attraction allow for that to happen. Now, you might be thinking, why is that? Right? Now, again, it has to do with those intermolecular forces. We think of water and oil. Water has hydrogen bonding. We know that's its strongest intermolecular force. Oil, on the other hand, is only going to have London dispersion forces. Well, since there are no attractive forces between water and oil that are going to compensate for the hydrogen bonds that are being broken in water, they just can't mix. The energy is too great for them to overcome, and a solution can't be formed, right? Now, for example, salts in water, what can happen there is you get the formation of ion-dipole interactions. In alcohol in water, you got hydrogen bonding and hydrogen bonding, so you get a solution being formed there. For benzene and oil, you've got two non-polar liquids that are interacting, so London dispersion forces get changed up, and they can form a solution. Now, I want you to think about this, and you might be thinking, Mr. Kenton, what does soap have to do with this idea of things dissolving? Well, when you start thinking about stains and things like that, typically a stain is caused by grease of some kind, something that's an oily substance, it's non-polar. And so when you think about that, that's why you can't just simply put a stain through water and hope that the stain comes out, because they don't share similar intermolecular forces of attraction. And so that's where a soap is going to come in, because what the soap is going to do is going to allow the water to penetrate and be able to extract the oil, because what the soap is going to do is it's going to interact with the non-polar components of, like, let's say the grease or the oil that's on a stain in a shirt, and it makes it so that the water molecules can then get in, surround the soap, and extract the grease. And in doing so, it removes that, cleans off whatever it is that you're cleaning, and then you've got a clean shirt or plate or whatever it is that you're working with. So intermolecular forces and this idea of solutions actually has an application for something you use every day. All right. Other solute-solvent interaction that I want you to consider, talk about the number of carbon atoms in a chain, how that affects solubility. We stated already that the more carbon atoms that the hydrocarbon has, the less soluble it's going to be in water, right? So here we've got some alcohols, and you've got the solubility of them in water and the solubility of them in hexane. So as you can see, our shorter carbon chains, 3 carbons or fewer, they have a really high solubility in water. But once we get to butanol, which is our 4 carbon chain and above, we start to see that the solubility of those alcohols decreases in water. whereas with our alcohols, they dissolve really easily in something like hexane. Now, the other thing we mentioned is that the number of OH groups that you have is going to increase the solubility in water. And so here we're taking a look at two different vitamins, right? Vitamin A versus vitamin C. So you can see vitamin A got a pretty long carbon chain, but notice that it's got this one lonely OH group, right? Whereas if we look at something like vitamin C, we've got OHs, 1, 2, 3, 4. We've got 4 OHs on one molecule of vitamin C. And so if you had to guess, you'd probably be able to determine that vitamin C is a water-soluble vitamin, whereas vitamin A is not. Okay, so that just kind of shows us that the more OH groups we have, the more soluble a substance will be. All right, now the next section we're going to be looking at is looking at how pressure can influence solubility. Now, a caveat here, pressure is only going to influence the solubility of a gas in a liquid, right? And that's because pressure only has an influence on gases. Pressure doesn't typically influence the condensed phases of solids and liquids. Now, when we start to think about solubility of a gas, it's going to be a function of the pressure of the gas. And a really good example of this would be something like soda, for example. Now, what we know about the pressure, how that influences solubility, is that the higher the pressure is on the gas, the greater the solubility of that particular gas. Now, I want you to think about this. You think about a soda, for example, or some sort of carbonated beverage, right? If it's in a bottle or if it's in a can, it's pressurized. And so what's happening is that high pressure is forcing the gas, carbonation, to stay dissolved in the solution, right? Well, you think about it. What happens as soon as you open a can of soda or you open a bottle of soda? It makes the nice little psst sound because it's releasing some of the gas. And so what we're doing is we're releasing the pressure, we're lowering it, so it's decreasing the solubility of our solution, so that gas has to escape so that it can get back to equilibrium, so that it can get back to the proper saturation point. Now, obviously, the lower the pressure, the lower the solubility on the gas. So again, I just want to reiterate, pressure is only going to influence gases that have been dissolved in a liquid. And you've got this relationship, the solubility of a gas can be determined based on the pressure of the gas times K, which is a constant. It's not a constant that's given to you, or actually it's a constant for each individual substance. You'd have to look up the substance specifically to get its value, and you could use that to figure out the solubility of the gas. All right, so if Sg is the solubility of a gas and K is a constant and Pg is the partial pressure of a gas, this was all determined based on the work of scientists, which we now call, this is Henry's law, which relates to us the relationship between the solubility of a gas and the pressure of a gas. All right. Now, the next thing we're going to take a look at is how does temperature influence the solubility of, let's say, a solid and the solubility of a gas? Because you think about pressure, it only influenced gases. It didn't influence solids. Well, so what we see here, if you look at these two things, these are solubility curves. You probably remember those from honors chem. Maybe they're bringing back flashbacks of maybe not positive memories, but maybe they are positive. I don't know. But what we see is that when we're talking about a solid, if you look at the graph on the right, or excuse me, the left, as temperature increases, what we see is that the solubility of a solid is generally going to increase. It's going to make the solid more soluble at a higher temperature. And that should make sense because what you're doing is you're adding in more energy, you're creating opportunities for intermolecular forces to be broken and new intermolecular forces to be formed, right? Now, sometimes you do see a decrease as temperature increases, like for the cerium-3 sulfate, but those examples are less common. Now, with gases, on the other hand, we see pretty clearly here that gases are going to be less soluble as temperature increases. And again, think about it. As you increase the temperature, you're increasing kinetic energy. Increasing kinetic energy, you're going to cause the gas to want to escape the surface of the liquid and not go back into the liquid. And so therefore, at higher temperatures, gases are less soluble. All right, now this leads us to our last little portion that we're going to look at today, is how do we express concentration? Now, we've been looking at solubility as this idea of how much has been dissolved to make a saturated solution, right? And so that's one aspect, but concentration is a way for us to talk about how much has actually been dissolved from a quantitative perspective, right? So some concentration units that you need to be aware of that you might have seen, like maybe you've taken AP Environmental Science, parts per million and parts per billion. Another thing is mass percentage, right? So mass percent of a component is going to be the mass of the component in solution divided by the total mass of solution times 100, right? Parts per million of a component, you take the mass of the component in the solution, you take the total mass of the solution, divide those two, and then multiply by 10 to the 6th, and that gives you your parts per million concentration. And then you got ppb, parts per billion. Take the mass of the component in the solution, divide that by the total mass of the solution, then multiply that by a factor of 10 to the 9th, and that gets you parts per billion, right? So these are all ways in which we can express concentration. While they exist, not something that we use very often in chemistry. Like I mentioned, ppm and ppb, those are very common in terms of environmental science. When you start looking at water quality or soil quality or air quality, you're going to start looking at things in terms of parts per million or parts per billion, right? Now, the concentration units that chemists use, well, as we see, are like mole fraction, molarity, and molality. And really, the one that we're going to see the most is molarity. So the one that has the R in it, molarity. Now, mole fraction, believe we've seen this previously when we were looking at Dalton's law of partial pressures. We looked at how you could use mole fraction times the partial pressure or the total pressure to get the partial pressure of a gas. But mole fraction, moles of component in solution divided by total moles of solution. Molarity, that's going to be the moles of your solute divided by liters of solution. That would be how you calculate the molarity. So moles of solute divided by liters of solution. And then molality, which gets abbreviated with a lowercase m, is the moles of solute divided by kilograms of solvent. And in seeing all these different units, they each have their own unique use. And like I mentioned, molarity is the one that we're going to be using most in AP chemistry. So looking at molarity is the thing that we need to be the most comfortable with. All right. And the nice thing about concentration, at least from a chemist perspective, is that we always want to be able to get into, in some senses, moles, right? Like if we can get to moles, we can figure out all sorts of different things. And so this just gives you kind of a little flow chart that shows you how you can move to different components in different concentration units. So here, like we're looking at molarity to molality, and we're looking at what we can use to figure out different components. So for example, if we have the volume of the solution in moles of solute, we can figure out the molarity. If we want to be able to move into the mass of the solution, if we know the density and the volume, we can figure out the mass, and we can kind of go from there to get into molality, if you will, right? So that's going to conclude this particular video. Thank you guys for joining me. Make sure you complete the Google form after watching this video. Let us know what your questions are so that we can address those in class. Thank you guys so much, and I'll see you guys again soon.